if we want to list a few moments of inertia, they're all obtained by integration, and generally Calculus 1 level integrations. As a matter of fact, it's standard in a Calculus 1 course, and if you had a Calculus 1 course through us on campus, you certainly were assigned moment of inertia calculations. You might not have understood what they meant because moment of inertia is, a little bit of a tricky concept. But it's just, you're basically integrating kinetic energies and the moment of inertia pops right out. Okay, moments of inertia. For a thin rod or beam rotating about the center, Y equals 1/12 big M, big L squared, M being the mass, L being the length. And I say thin uniform rod or beam, since you have, since you need a constant mass density to do that integral. Now, if you have a mass density that isn't constant, well, you got to throw that into the integral, and you're going to get a different result. But it's a simple integral, assuming your mass density function is simple. Okay, thin uniform rod or beam, moment of inertia is 1/12 ml squared, and then if it's rotating about an end, and I'm not going to write this down, I'm just going to say it, but okay, for example, if this is treating this as a pendulum, you're going to want to analyze the moment of inertia, and if it's pendulum being suspended from one of its ends, then it's rotating about that end. It's not rotating all the way around, but there is rotation about the end. Your moment of inertia is going to be 4 times as great. That's because every chunk of mass is twice as far, and the distance ends up being squared. Now, I could give you a much better argument for that, but just if every increment of this thing is twice as far from the axis of rotation as it would effectively be about the center, and I don't want to go into too much detail about why I say half as great, but you see that the average distance of every mass from the center is half as great as the average distance of every mass from the end. Well, that means that this L thing averages twice as great, so when you square it, it averages 4 times as great. So anyhow, it's going to be this. Which is 1/3 ml squared. Okay? Without going any further into the reasons for this, you can also set up the integral. The integral would go from 0 to L, and if I had done the integral from 0 to big L, I would have ended up with 1/3 ml squared. So it's very easy to do that integral. And very easy to adapt what we saw there to what's going on here. Okay, so a uniform disk rotating about an axis through its center and perpendicular to the plane of the disk. Now, when I say that, let's be careful about what we mean. I'll use this as a prop. It's not a disk, but imagine this is a disk, and you're rotating this way. Okay, then you got the disk rotating about an axis through the center, perpendicular to the disk. If it's rotating this way, the moment of inertia is going to be different. Okay, and we say then that the axis goes through the center, but it's in the plane of the disk. Okay, now if you got a rectangular object like this, you could rotate about an axis in the plane through the diagonals, through the center, this way or this way, about one of the ends, and you could do the same. You could do it with the disk about one of the edges. Okay, so there's a lot of different variants on this, and you can look up formulas for these things. They're all over the place. Just look up moments of inertia, you find all kinds of formulas. Okay, but anyhow, for a uniform disk rotating about the center, about an axis through the center, perpendicular to the plane of the disk, I equals 1/2 ml squared. Make that m a little higher to make it look like that's not part of the denominator. That's a really bad m, but you should understand what it means. Okay? A uniform sphere rotating about an axis through the center. It's not 1/2 ml squared, it's 2/5 ml squared. Now, comparing the 1/2 here and the 2/5, you see that's 0.5, that's 0.4. This is a little bit less than this. And the reason for that is, if you got a disk, a flat disk, the average position of the masses in that disk relative to the center is a little different than it is for the sphere, because the sphere is thicker toward the axis of rotation than it is toward the edges. And the closer the mass is to the axis of rotation, the less its distance from the axis of rotation, obviously, and the less its squared distance, so the less contribution it makes to the moment of inertia, so that the moment of inertia of the sphere is a bit less than the moment of inertia of a disk of the same radius, and I'm using L, so that was, okay. So for a sphere and a disk of the same radius and same mass, of course they'd have to have different mass densities, but the sphere is going to have only 80% the moment of inertia of the disk. Which means that if the sphere and disk have equal masses and radii, it's going to take less energy to get the sphere rotating at a certain rate than it does the disk. If those gestures make any sense, I'm not sure they do. Well, these are kind of 4 fundamental moments of inertia. Others are a little more complicated. These are easy to remember, and I expect you to use them and remember them. And to remember them, you got to understand you're going to have a mass times some dimension squared, and you're going to have some fraction, and the fraction comes out of an integral. And these are all simple integrals. The hardest integral is this one, where you got to use a shell method of integration. something you've seen, something you hear the name of and probably shudder a little bit, but it's not that bad, and you really need to use this course as a way of kind of cementing that bit of knowledge from calculus, because that bit of knowledge is very important if you're in a STEM, a mathematically rigorous STEM curriculum. Okay, well, there we have it. Those are moments of inertia. Now I want to return to the question of energy and energy exchanges. And also, well, let's just ask the question, okay, you've got this beam, and we're going to have it rotating about an axis through its center, unless we use it as a physical pendulum and suspend it. We're going to do that too. So here it is. But we're also going to have things attached to it. You know, in the example I used, we had one of these attached to it, and you probably want to use rubber bands to do that. Because you could also do it with magnets, but you're going to be using the magnets for other things. So we might have one of these things here. Now, to keep the system in balance, we're going to have one over here. Otherwise, the system gets a little lopsided. And any measurements that you make of its motion are going to be interfered with by the tendency of an unbalanced beam to go into simple harmonic motion and not go through a complete revolution. And even if it does go through a complete revolution, that tendency towards simple harmonic motion is going to distort your data. Okay, so we've got to be careful about that. Okay, so anyhow, we have this and this. Okay, well, each of these things has a moment of inertia about its center. So let's just say moment of inertia about the beam is 1/12 ml squared, and the moment of inertia of each of these has a moment of inertia about its center of mass. And we're going to assume these are uniform. Just think of this, where the center of mass is the geometric center. We'll call that a rectangle. Moment of inertia of the rectangle. Here and here. Now that's a moment of inertia about its center. Of mass. That's not its moment of inertia about this point. So the question is, how much does this and this, we assume they're identical, how much does each of these contribute to the total moment of inertia of our rotating system, because they're not part of the system? Okay, well, should have written down the mass, and I didn't leave myself room. Okay, I'll call that mass M rectangle, M rect. And moment of inertia about the center of mass. Each of these has a mass M rect, in some moment of inertia about its geometric center, its center of mass. And let's just say that the center of mass is at distance I'll do R, capital R, with a subscript of RECT for rectangle. From the axis of rotation for each of them. Well, then the moment of inertia of the system is moment of inertia of the beam plus the moment of inertia of the rectangle about its center of mass plus I'm going to write it down twice. So you have an MR rectangle squared for this one, and an MR rectangle squared for this one. So what you end up with is the moment of inertia of the beam plus the moment of inertia of the rectangle plus 1/2 m times the square of the moment of inertia of the rectangle. Now let me digress to something maybe I should have done earlier. Got an axis of rotation and a particle of mass m and some kind of a massless rod. We'll make that mass a capital M. And this distance here is R. Axis being here. At angular velocity omega, the speed v of the mass, and I'm going to take that to be implicit, is r times omega. And we know that quite well, so it should be very clear that we're talking about the mass at this point. So kinetic energy, 1/2, the whole mass is moving at that speed, so there's no mass moving at any other speed. So kinetic energy is 1/2 the mass times r omega squared. So it's 1/2 mr times omega squared, which is 1/2 I omega squared, where I equals mr. Now, if you have a circular array of masses, with a bunch of massless rods, each of mass little m, then, looking at the time, circular array particles, each of mass little m, massless rods, your moment of inertia is going to be the sum of mr squared, and r is the radius of this circle. It's the sum of your mr squareds, but the r is the same for every one of them. So you have the sum of m, small masses, times r squared, which is big mr squared. I didn't put the square on this r here. Obviously, you need a square. When you square the r here, you get a square and so forth, okay? So, from this, you see that each of these masses has moment of inertia little mr squared, so that r being constant, you can pull that out of the expression, and you have the sum of the m times r squared, which is big mr squared, where big M is the total mass. Okay? That should give you a convincing argument that the mass for a uniform hoop every particle in this hoop, a hoop being something that just has mass along its rim, no mass inside or outside, uniform hoop of mass big M, radius r, you could sum up all the moments of inertia of all the particles in this hoop, just as we did here, and you would get the same result, that the moment of inertia is big M times r squared. So there we have it. And actually the hoop doesn't even have to be uniform. although if you're going to rotate it with any speed about the center, you kind of hope it's at least balanced, because this whole thing doesn't assume that these things are even equally spaced. Just got that many of them around the rim. Again, if you're designing it for any practical purposes, you probably want it to be pretty uniform. Okay, so here's another formula for moment of inertia. It's just common sense that comes out of this simple development. For a single particle at radius r, this is going to be your moment of inertia. So for any collection of particles, all at radius r, it's going to be the same, where big M is the total mass of all the particles. And that's especially true of a hoop. Okay, well, there are moments of inertia, and this is how you get the moment of inertia of a combined system. Now there's a basic principle here, parallel axis theorem, that you'll see in your work. So you want to understand this example, which makes a parallel axis theorem a whole lot easier to understand. It's kind of abstract the way it's usually presented, but if you just think of the beam with a couple of these things at the ends, you can make sense of it.